Good afternoon, Internet. I am Matt Booyak, and in this video we'll be taking a look at the 50th problem from the Project Euler Problem Archive. Now, this problem asks us to find the longest series of consecutive prime numbers which add up to a number less than 1 million that is also prime. Now, the approach that we're going to be taking for this problem is pretty straightforward. We're going to consider all the possible lengths of series, starting at 1 and going up to however many primes it takes to add up to 1 million. And then for a given series length, we'll be considering all the possible series with that length up to the largest one that, again, adds up to less than 1 million. Then we'll calculate the sum of each of those series and find the one which is longest and adds up to a prime. Now, at first glance, this sounds like it could be an order n cubed algorithm. That is, that the total number of possibilities that we have to consider, or the total number of steps that our algorithm has to take, seems like it might be proportional to the cube of our upper bound. And since our upper bound is 1 million, the cube of 1 million is quite large. If that were actually the case, it would certainly be fatal to our effort. But there are a couple reasons why this algorithm actually performs much better than you might expect. In some ways, it's like the opposite of problem 44, where the most natural algorithm turned out to be a monster, while the most natural algorithm in this case actually performs much better than you might expect. And the first thing we can do is that we can actually avoid calculating the sum of each individual series independently. And to show you an example of how that can be done, let's consider the example given by the problem description. So here we have the sum of the first 6 primes, and let's suppose that we want to determine the sum of primes 2 through 7. Well, we could add the second prime and the third prime and the fourth prime and the fifth prime and the sixth prime and the seventh prime, or we could take the fact that we know that these primes add up to 41, and we could subtract 2 and add the next prime, which is 17, to get 56. And that's a much more efficient way of computing the value of a particular series based on the one just before it. In fact, no matter how long we make this series, we can still do that computation in just 2 steps. It's independent of the length of the series. Now, even so, you might think that this is still something like an order n squared algorithm, and 1 million squared is still quite large. But remember, surprise, surprise, there aren't 1 million primes less than 1 million. In fact, it's not even close to 1 million. So to get a better idea of exactly how our algorithm is going to perform, let's actually jump over to Wolfram Alpha. I've never used this, as I can recall, on the channel. But it's really useful for getting some just quick and easy results. So we can ask it, how many primes are less than 1 million? And it tells us that there are roughly 80,000 primes less than 1 million. So much less than 1 million. Now, if our algorithm was still had a running time proportional to the square of the number of primes, that would still be pretty bad. But remember, we're not actually going to have any series of length 80,000. It will take far fewer than 80,000 primes to add up to 1 million or more. In fact, we won't have any series of length 70,000 or 60,000 or 50,000 or 40,000. Let's see, how many primes does it take to add up to 1 million? Let's say, what is the sum of the first 1,000 primes? And you see that we're already well past 1 million. In fact, we can try sum of the first 500 primes. Sum of the first 500 primes. There we are. A little bit less than 1 million. Suppose we try 600. We're over. 550. Nope, I mistyped. And you can see we're just a little bit over 1 million. So roughly the first 550 primes are going to add up to more than 1 million, which means that we will never have a series which is 550 primes or longer. And it gets even better. This is only assuming that we start with the very first prime, that is with 2. What if instead of looking at the first 500 primes, we look at primes 1001 through 1500? So we can say sum of the first 1500 primes minus sum of the first 1000 primes. And you can see that we are well over 1 million. We're over 5 million. So let's try cutting this down to 250. Still well over 1 million. Maybe we'll cut this down to 1100. Under 1 million. Wait, did I make a mistake there? Did I make a mistake? Yes, or no, I did not. We're fine. In any case, roughly 150 primes or fewer at that point are required to hit 1 million. So you can see as we increase the value of our first prime, the number of primes we can put in our series drops dramatically. Now, ideally, we would calculate a precise formula for what exactly the running time is for our algorithm as a function of our upper bound. But it turns out that the primes aren't the most well-behaved things in the universe. In fact, if you're able to bring order to the primes, there is literally $1 million prize waiting for you. Now, there are some very good estimates for the distributions of the primes, and so we could probably come up with a good estimate for our running time. But I'm not going to do that in this video. I think that my guess is that it's probably something like n over log of n times the log of n, or something bizarre like that. I haven't actually worked it out myself. If you're curious, maybe I can do an extra video where I compute that. If you'd like that, maybe leave me a comment below. But I think we've gathered enough evidence that we can say that our algorithm will probably be efficient enough. So let's get to writing some code. Let's copy our template directory to make our problem directory. Enter our problem directory and open our main.cpp. Okay. We will need to include our primes class because we're going to be doing some work with primes. We'll need to update our make file to include our number theory library, which has the primes class. And then I want to just declare a little structure here. We'll call it seek, or series, perhaps, which is going to describe a particular series for us. Keep in mind, we only need to know the index of the which prime is the first element and which prime is the last element in our series. And then we'd also like to keep track of the sum. Okay. Okay, so we're going to start off with our series. We'll say struct series first k. So that's going to be the sum of the first k primes. This will be useful so that we don't have to recalculate that every time we start over with a series of a different length. And that's going to start off at the index 0 and 0 with a sum of 2. That is, the first prime is going to be the only prime in the series, and that has the value 2. We will need to declare an instance of the primes class for doing calculations involving primes. And so now I think we can do our loop. So we'll say while first k dot sum is less than 1 million. That is, once the sum of the first k primes exceeds 1 million, we don't have to consider any more possibilities because they will all add to more than 1 million. Okay, we do want to, at the end of this loop, update our first k series. And we're going to do that by adding the next prime in the series. And so we'll say first k dot last, and we'll say first k dot sum plus equals p dot get prime, and we're getting the first k dot last prime. Just an example to make sure that we did this correctly. On the first iteration, this will be 0. We'll increment it to 1, and then we will add the prime that has index 1, which will be 3, to give us a new sum of 5. So that's just as we expect. Okay, so then we want to have a series which we'll call cur k. So that's the current k primes that we're looking at. And actually, we're going to start that off as being a copy of first k. Okay, and then we want to say while cur k dot sum is less than 1,000. Excuse me, 1 million. Okay. And to advance our sum, you'll recall that we want to remove the first prime and add the prime 1 past the last. And so we'll say cur k dot sum minus equals, let's see, p dot get prime cur k dot first. Then we'll say plus plus cur k dot first. And then we will say plus plus cur k dot last, so advancing the end of the series. And then we'll say cur k dot sum plus equals p dot get prime cur k dot last. And of course, we also want to check if we actually have a solution. So we need to do if cur k dot sum is a prime, so we'll say p dot is prime cur k dot sum. Printf. Let's see. We'll do %d is the sum of %d consecutive primes. And that's just going to be cur k dot sum and cur k dot last minus cur k dot first plus 1. You'll notice that we have this plus 1 because, for example, if last was 2 and first was 1, that refers to 2 different primes, but last minus first would only give us 1. And so we have to add 1 to get the right answer. Okay. Let me just look over this for a moment. I think that should be everything. And so this is going to print out all of the series that we find. We can actually put in here, once we find a series of a particular length, we don't have to consider any more of that length. There's no bonus for having a greater prime summing from a series of the same length. So we can just break at that point. Okay, let's go back to our shell and make. Looks like I forgot something here. It's on the 22nd line. Oh, I just missed a comma. Okay, so we get 997,651 is the sum of 543 consecutive primes. So we'll go back to our, oh, I hate it when that happens. There's a lot of garbage here today. So we'll go back to our archive here and sign in, because I always have to sign in. Then we'll scroll down to problem 50. In the future, we'll have to go to page 2 as well. We're at the bottom of the first page. And we'll see that that does, in fact, match our answer. So as always, thank you very much for joining me. Tomorrow, we'll be doing problem number 51.